Hello everyone tonight. We're not just watching a story, we're stepping into one. We're going to drift back in time to an era of bell-bottoms and rotary phones, to a world caught between a simmering Cold War and a cosmic optimism. This is the story of two little machines launched from a planet you and I call home on a journey that would redefine our place in the universe. They were named Voyager, and they were designed to take a look at our neighborhood before heading into the great quiet unknown. Now, before you go and watch, please take a moment to like and subscribe to this video, but only if you truly enjoy what I do. And if you're comfortable, feel free to let me know in the comments where you're listening from and what time it is where you are. Are you in a city that never sleeps, or are you curled up in a quiet corner of the world just as the moon begins its slow ascent? As the music fades, imagine yourself not in a chair or on a bed, but in a small cramped control room in California in the 1970s. The air smells of lukewarm coffee and burnt circuit boards. The lights are low. The tension is high. You're watching the final frantic preparations for a launch that feels both impossible and inevitable. It's a mission that has been scaled back, re-envisioned, and almost scrapped 100 times. A mission that will not carry a single human being, but will carry the best of us wrapped in a thin layer of metal and gold. In the decades leading up to this moment, a great cosmic race had consumed the world. It began in the late 1950s, not with a bang, but with a simple, unnerving beep. The Soviet Union had launched Sputnik, a tiny metallic sphere that did nothing more than orbit the Earth and broadcast a signal. But that signal was a profound geopolitical statement. It said, "We are here, and we are ahead." The United States responded with a fervor fueled by fear and national pride. The space race was on, and it was a competition not just for technological supremacy, but for the very soul of the 20th century. You were probably a child, or not even born yet, but you know the stories. The flickering black and white images of Alan Shepard, the first American in space. The audacious dream of President John F. Kennedy, who stood before a nation and declared that humanity would reach the moon by the end of the decade. And then, the climax, Apollo 11. It was an ethereal moment, almost too perfect to be real. A grainy image of a man bouncing on the lunar surface, a voice crackling across millions of miles, saying those immortal words, "One small step for man, one giant leap for mankind." For a brief shining moment, the entire planet held its breath. It felt like anything was possible, like the sky was not a limit, but an open invitation. But history, as you know, is a fickle thing. The Apollo program was a spectacular, breathtaking peak, but it was also a finale. The public, having seen the moon conquered, began to look elsewhere. The cost was astronomical. The political will began to wane. Budgets tightened. Missions were canceled. NASA, the agency that had just achieved the impossible, now had to look at its empty dance card and ask, where do we go from here? And the answer was as simple as it was audacious. We go farther, out past the known worlds, past the familiar red dust of Mars and the scattered rocks of the asteroid belt. A family of giants awaited. Jupiter, Saturn, Uranus, and Neptune worlds, too distant, too mysterious, and frankly too large for the early space programs. They were just fuzzy dots in a telescope's celestial whispers, wrapped in clouds of methane and hydrogen. For decades, they remained largely untouched and unseen. Beautiful enigmas waiting for an introduction. The timing, as it turned out, was perfect. Almost once every 175 years, these outer planets align in a rare and beautiful cosmic ballet. It's a moment when a single spacecraft, if launched with perfect precision, could use the gravity of one planet to slingshot itself to the next, like a stone skipping across a pond. This maneuver, known as a gravity assist, wasn't just a clever trick. It was a way to save unimaginable amounts of fuel and time. It was a golden ticket, a secret passageway through the solar system that would only be open for a brief window in the late 1970s. The idea was born in the 1960s, a concept so grand and ambitious, it was simply called the Grand Tour. The The plan was lavish multiple probes, each visiting a different set of planets, perhaps even Pluto. It was a project born of boundless optimism, a dream that fit perfectly into an era that had just sent humans to the moon. But by the 1970s, that optimism had faded. The calculators in Congress began clicking, and the grand tour was deemed too expensive. It was quietly shelved, a beautiful but unfeasible dream. But a dream, like a seed, doesn't always die when it's buried. Instead, it adapts. It mutates. A new, more modest concept emerged, built on the bones of the grand tour. This was the idea for Voyager. Instead of multiple probes, they would build two. They would be twins identical in design, built with a simple elegance and a rugged durability. Their goal was a little more humble. Just get to Jupiter and Saturn. Anything beyond that would be a bonus, a stroke of good luck. And with that humble hope, amidst the rise of disco music and the glow of cathode ray tube televisions, work began on what would become the longest operating spacecraft in human history. It's worth pausing here to consider the raw courage of this decision. This wasn't a mission with a guaranteed climax, no flag planting, no triumphant return. This was a mission about endurance, about sending a part of ourselves into a slow, patient, and quiet journey with no destination in mind beyond the known. The Voyagers wouldn't carry people, but they would carry everything humanity knew about spaceflight and science. They would carry our best parts, our curiosity, our hope, our need to explore, even when no one else is watching. The teams at NASA's Jet Propulsion Laboratory, a place that always seems to hum with a quiet, focused energy, were not just building machines. They were building time capsules. A testament to a moment in history when, despite political divisions and technological limitations, we still looked up at the stars and asked, "What's out there?" They were working on a project that bordered on science fiction, built with the humble tools of their time. The outer planets were still mostly fuzzy dots. Neptune was just a name. Titan was just a shadow. And yet, there was an unshakable belief that we could get there, that with enough math patience and perhaps a touch of luck, we could build something that would outlast us, something that would keep going even when we stopped listening. As the 1970s rolled on and the launch window drew closer, the work became a frenetic dance of data tables and daydreams of poetry and plumbing. Engineers debated thermal shielding and camera calibration. Artists selected images. Scientists planned trajectories. It was the space program's version of a masterpiece, created with both the cold logic of an equation and the soaring ambition of a symphony. And it wasn't born out of triumph, but out of a longing, a need to keep reaching outward after we had already touched the moon. And perhaps that is why they still resonate with us. Because in a world filled with noise and distraction, the Voyagers remind us of something quieter, something enduring, the gentle, persistent pulse of curiosity that keeps asking, "What's out there?" And so, with fuel-loaded cameras ready and the golden record secured in its protective case, the Voyagers stood poised on the launch pad. They were twin time travelers, not destined to return, but destined to remind us what it means to leave. Designing something to last more than 40 years is ambitious under any circumstances. Designing something to survive for that long in deep space, with no repairs, no pit stops, and no second chances. That's not just ambitious. That's a testament to human ingenuity. You're watching as they stand there now, two silent sentinels bathed in the Florida sun. The air is still heavy with a humid silence. You can hear the distant hum of the machinery, the quiet chatter of the launch crew, the soft whoosh of a breeze. It's not the dramatic countdown of a movie. It's a slow, patient moment. And in this moment, you feel it. That same hope that fueled a generation of dreamers. The hope that these little machines built from wire and metal might actually make it. That they might actually tell us something new. It's a story about persistence, about the quiet power of a long view, about the belief that even in the vastness of space, a tiny signal from home can be the most profound thing of all. And it's about to begin. The launch window is open. The universe is waiting. You're still there in the quiet hum of the workshop watching them take shape. Not as gleaming spaceships from a sci-fi movie, but as something more pragmatic, more human. The Voyager spacecraft weren't built in a clean room that felt like a surgical theater. They were built in a world of clunky terminals with green text flickering on black screens. A world where computers had less memory than the simplest smartphone app you use today. It was a time of slide rules and soldering irons, a period of brilliant minds making do with what they had, and doing so with astonishing grace. The engineers, the unsung heroes of this story, were less like magicians and more like master watchmakers. Their challenge was not to create something new out of nothing, but to take existing proven technology and make it work perfectly in a hostile environment for a mission that would last far longer than anyone had a right to expect. It was a philosophy of keep it simple, keep it sturdy. They knew these ships would be far beyond the reach of any wrench or screwdriver after launch. Everything had to be just right the first time. Consider the computers on board. You're a child of the digital age, surrounded by teraflops of processing power. But imagine a computer so primitive, its memory was measured in kilobytes, thousands of bits of information, not billions. The Voyager's main computer, the Flight Data Subsystem, FDS, had about 69 kilobytes of memory. To put that in perspective, the average JPEG photo on your phone is probably a few megabytes thousands of times larger. The engineers had to write code so compact, so elegant, that it could fit into a space that, to us, feels almost comically small. They were poets of code, turning every single byte into a line of verse. The design itself was a work of art, born from practicality. Each Voyager was a spindly creature, like a celestial praying mantis. It was a central hub of instruments, with long booms and antennas jutting out. There was the 12-foot high-gain antenna, a parabolic dish that would serve as the spacecraft's voice and ears its lifeline to Earth. It was so powerful that it could whisper a signal across billions of miles, and our giant dishes back on Earth would be able to hear it, a testament to the elegant physics of radio waves. One engineer I remember reading joked that it was so precise it could have been used to aim a laser beam at a quarter from a mile away. Then you have the booms. One held the magnetometer, a delicate instrument designed to measure magnetic fields, a gossamer thin limb extending out to avoid interference from the spacecraft's own electronics. The other held the cameras and other instruments. And at the end of another arm was the most critical part of the whole machine, its heart. Not a beating flesh and blood heart, but a nuclear one. The radioisotope thermoelectric generator, or RTG. This was a major point of discussion in the design. Solar panels, the obvious choice for most spacecraft, wouldn't work. The Voyagers were headed to the dark, cold outer solar system, where sunlight is too faint to be useful. So they turned to a different kind of power, the slow, inexorable decay of plutonium. The RTG wasn't an engine. It was a simple, brilliant heat source. It used the natural heat from the radioactive decay of plutonium-238 to create electricity. It was a silent, patient power source designed to last not for a few years, but for decades. And that decision, that leap of faith in a simple, reliable power source, is why we are still listening to the Voyagers today. There's a well-known historical fact that the Voyager project was almost not greenlit. It was born from the ashes of the much larger, more expensive Grand Tour proposal. What is perhaps less known is that even after the Voyager concept was approved, it was a constant battle for funding. The engineers had to be not just brilliant scientists, but savvy salesmen constantly justifying their work, proving that every dollar was essential. They had to build a spacecraft that was beautiful in its simplicity, elegant in its function, and cheap enough to get past a congressional committee. The construction process was a symphony of precision. You can watch them now in your mind's eye as they carefully attach each component. They use special tools to tighten bolts with a perfect measured torque. They carefully lay out the miles of wiring each cable a vein carrying lifeblood to a sensor or a camera. They're working in a clean room, yes, but it feels less like a sterile lab and more like a sacred space. They know that every tiny screw, every soldered connection, every line of code has to be flawless. Because in the deep dark of space, there is no one to fix your mistakes. You can almost hear the soft click of a camera lens being mounted, the gentle hum of a gyroscope being calibrated. The spacecraft feels fragile in your mind, but you know it is anything but. It is a work of rugged resilience, designed to withstand the violent shudder of launch, the punishing cold of deep space, and the fierce radiation belts of Jupiter. It's a beautifully complex machine, but it's built on a foundation of simple, elegant principles. And they were built to be twins, but they were also given slightly different missions. It's like they were born with a predestined separate path. Voyager 1 was designed to make a close pass of Jupiter and Saturn, then head out of the plane of the solar system, where it would get a unique view of the heliosphere. Voyager 2, on the other hand, was given the longer, more ambitious journey. It would visit not just Jupiter and Saturn, but also Uranus and Neptune, taking advantage of that rare alignment. It was the longer, more arduous journey, and it was a gamble. What if something failed? What if a single component gave out billions of miles from home? That gamble, that hope, is a central theme in the story of the Voyagers. It's a testament to the fact that great science often requires a leap of faith. The engineers and scientists had to trust their math, trust their tools, and trust their own ingenuity. There were no do-overs. The famous academic debate, still ongoing in some circles, revolves around whether the team should have built a more robust backup system, or if their minimalist, less is more philosophy was the only way to get the project approved and off the ground in the first place. Some argue that a bit more redundancy could have saved some of the instruments that eventually failed. Others say that any extra cost or complexity would have sunk the project from the start. You can't help but feel a certain affection for these machines. They feel like a child's toy that has been given a great and serious purpose. They are not sleek and modern. They are all sharp edges and exposed wires, a product of their time, but their very lack of high-tech gloss makes them feel more real, more accessible. They remind you that great things are not always born from perfection, but from the earnest, diligent work of people who believe in an idea. The final touches are being made. The golden record is carefully placed in its protective casing. The instruments are sealed. The spacecraft is given its final, once-over last silent blessing before it is prepared for launch. You watch as a small team of technicians gently, reverently move it from the workshop to the launch facility. It's a slow procession, a moment of profound quiet before the thunderous roar of the rockets. They are sending their creation, their silent ambassador, out into a great unknown, and you can feel the weight of that moment. The decades of work, the millions of calculations, the hopes and dreams of a generation, all riding on this small, delicate-looking machine. It's a moment of quiet reflection, a deep breath before a long dive. You are about to send a piece of yourself, a piece of us all, on a journey of no return. You're not just launching a rocket, you're launching a story that is just beginning. You're watching the Voyagers, those spindly metallic insects, being carefully wheeled out of the workshop. They are just machines, you remind yourself, a collection of wires and sensors and antennas. But you know that's not quite right. Because bolted to the side of each one, encased in a protective aluminum jacket, is a disc. It's a gold-plated copper record, and it holds a message from us to the universe. This is the story of the Golden Record, and it is perhaps the most audacious act of poetry in the history of science. The idea for the record was born from the mind of Carl Sagan, an astronomer and science communicator, who believed that a spacecraft traveling beyond the solar system had a unique opportunity. He reasoned that if the spacecraft were going to leave the sun's influence forever, why not attach a message, a greeting card, a bottle cast into the cosmic ocean, a time capsule not for our descendants, but for something else entirely. The odds of it being found were, to put it mildly, microscopically small. The galaxy is enormous, and Voyager is just a speck of dust traveling through an unimaginable void. But the point, as Sagan knew, was not the likelihood of contact. The point was the gesture. The team he assembled was a strange and wonderful mix of scientists, artists, and thinkers. They had a seemingly impossible task to represent the entirety of human life and culture in just over an hour of audio and a handful of images. And they had to do it fast. The mission was already underway. They had only a few months to gather content, decide what to include, and physically produce the discs in time for launch. It was a mad dash of creativity and curation, and you can imagine them working day and night in a small cluttered office, debating what sounds to include, what music to select, what pictures to represent our species. The most famous part of the record is the collection of greetings. These weren't just formal messages from dignitaries. They were greetings in 55 different languages, a celebration of our linguistic diversity. You can hear them now echoing in your mind. The ancient languages like Akkadian from Mesopotamia sound like whispers from a long-lost past. The modern ones like English and Mandarin feel like a snapshot of our current moment. And some are just beautifully simple, like the greeting in English from a young child's clear voice, "Hello from the children of planet Earth." It's a statement of innocence and hope, a sound that says, "We are small, but we are here." But they didn't stop at words. The team wanted to capture the very essence of our planet. They included a vast array of natural sounds, a kind of sonic collage of Earth. You can hear the roar of surf, the rumble of thunder, the cry of a loon, the song of a humpback whale. One particular sound, a recording of a kiss, feels so deeply, wonderfully personal. It's a sound of affection, of connection. Something that an alien species might not understand scientifically, but might perhaps feel on some level. There's a certain poignant truth in the fact that humanity's first message to the stars included a baby's cry and the sound of a Saturn V rocket lifting off two noises of immense power, one of birth and one of ambition. Then came the music, a cosmic mixtape designed to show not just what we listen to, but what we feel. The selections were breathtaking in their diversity, from a Bach-Brandenburg concerto to a Navajo night chant, from an Indonesian gamelan piece to a Peruvian wedding song. There was a Japanese shakuhachi composition and the famous Blind Willie Johnson blues song, "Dark was the night, cold was the ground." Carl Sagan once said that this song, with its wordless, mournful moans, expressed the human condition better than any spoken language could. It's a sound of loneliness and longing, a beautiful, haunting sound that feels at home in the vast, cold emptiness of space. You might be surprised to learn that one very famous piece of music was left off the record due to a rather mundane reason. The Beatles wanted to include their song, "Here Comes the Sun," but rights issues and record label bureaucracy prevented it. This tiny human detail, the fact that even our most ambitious message to the stars could be thwarted by copyright law, is a bit of quiet cosmic humor. It's a reminder that even at our most poetic, we are still so very human. In addition to the audio, the record held 116 images encoded in an analog format. These images were a visual introduction to our species. There were pictures of landscapes, animals, human anatomy, and people engaged in everyday activities, eating, dancing, a mother nursing her child. There were also scientific diagrams, pulsar maps designed to give the finder a galactic address for our sun, and a representation of our solar system's planets. If an alien civilization with a grasp of physics were to find this disk, they could in theory decode its language and begin to piece together a story of who we are. One of the most profound and personal inclusions was a recording of a human brain. Not just any brain, but the brain of Anne Druyan, a member of the production team who would later marry Carl Sagan. For an hour, electrodes recorded her brainwaves as she meditated on a wide range of ideas, including the history of Earth, the nature of humanity, and the experience of falling in love. That raw data was encoded onto the record, a mental fingerprint of a human in a state of deep reflection. Somewhere out there in the deep dark, a heartbeat of human consciousness continues to travel, a whisper of love and thought, reaching into the black. The academic debate that swirls around the golden record is a fascinating one. Some scholars and scientists argue that it was a foolish and perhaps dangerous thing to do. They contend that we as a species are not ready for a first contact scenario. What if the civilization that finds it is not benign? The golden record, after all, includes a map to our home. Other scholars, and Carl Sagan among them, believe that the act of sending the record was more important than the potential for contact. They argue that it was a declaration of our existence, a statement of our desire to connect. It was an act of hope, not of fear. They believe that any species advanced enough to find and decode the record would, by their very nature, have moved past aggression and violence. You watch as the final checks are made. The record is sealed, the cover locked down. It is a work of immense care and profound thought, a small golden island of sound and image traveling through an ocean of emptiness. It's a piece of us, not the technology that we are proud of, but the art, the music, the feeling. It's not a message for a species. It is a message for the universe itself. And now the spacecraft are ready. The record is in place. The long journey is about to begin. You feel a sense of calm, a sense of rightness. This is what we do as a species. We explore, we tell stories, and sometimes we send a bottle into the cosmic ocean, not because we expect an answer, but because it feels important to say something, to say, we were here. This is who we are. And we said hello. The Florida sun is a relentless humid blanket, but here on the launch pad, you don't feel the heat. You feel the anticipation. The air crackles with an energy that is both physical and intangible. It's the energy of 1,000 brilliant minds, 1,000,000 hours of work, and the silent collective hope of a generation. The rockets, a Titan-Centaur combination, stand tall and proud, holding the precious cargo of our dreams. You are here watching, not as a spectator, but as a silent participant in one of the most remarkable acts of choreography ever conceived, the Voyagers. Those twin metallic sentinels aren't just going to be thrown into space. They are going to be placed on a cosmic highway, a route charted with an almost impossible precision. They are about to begin a journey that is less like a car ride and more like a celestial game of pinball. Each massive planet, Jupiter, Saturn, Uranus, Neptune, is a gravitational flipper designed to give the spacecraft a precisely timed push, accelerating it and flinging it toward the next destination. This technique is known as a gravity assist, and it is the key that unlocked the outer solar system. Think of it this way: a spacecraft doesn't just need speed, it needs direction. To get to Neptune billions of miles away, you would need an absurd amount of fuel to constantly fire your engines and adjust your course. The gravity assist solves this problem. As the spacecraft approaches a giant planet, it falls into the planet's gravity while speeding up as it plummets toward the surface. But instead of hitting the planet, it swings around it like a stone around a giant boulder, and then exits the other side, now moving faster than it was before, relative to the sun. It's like borrowing a tiny bit of the planet's momentum, and in return, the planet doesn't even notice. It's an elegant, fuel-saving, and breathtakingly clever maneuver that made the Grand Tour possible. But to pull off this trick, the timing had to be perfect. The launch window was narrow, and a delay of even a few days could have meant a complete failure. And this brings us to one of the most intriguing and often confusing facts about the mission. You would think that Voyager 1, the first one, would launch first. That makes sense, right? First is number 1. But space exploration doesn't always follow tidy numerical rules. In fact, Voyager 2 was launched first on August 20th, 1977. Voyager 1 followed just 16 days later on September 5th. The numbering had nothing to do with the launch order. It was based on their planned trajectories and which one would reach its target planets first. Voyager 1, with a sharper, more direct path, was set to arrive at Jupiter and Saturn sooner than its sibling. So numerically speaking, it would be the first to explore. A bit confusing perhaps, but hey, naming conventions in space have always had a little poetic license. The academic debate about this particular decision still lingers in some corners of the scientific community. Some argue that because Voyager 2 was the one with the more ambitious full tour mission, it should have been given the fastest, most direct route to ensure its success. Voyager 1, in this view, was the backup that got to the planets faster. Others argue that the decision was a stroke of genius. It allowed them to send the scout Voyager 1 first to gather data and verify that the gravity assist maneuvers would work as planned. This gave the team valuable information before the more critical long-haul Voyager 2 took its shot. It was a calculated risk that ultimately paid off beautifully, but at the time it was a decision that kept many engineers up at night. As you stand there watching the final preparations, you can feel the weight of this gamble. It's a leap of faith not just in the technology, but in the immutable laws of physics. The navigation teams had to calculate the spacecraft's paths down to fractions of a degree. A tiny error in trajectory at Jupiter could mean completely missing Saturn, let alone Uranus and Neptune. These weren't remote-controlled toy cars. Once they were on their way, they were on their own, guided by pre-programmed instructions and the gentle, invisible hand of gravity. The launches themselves were not the dramatic televised spectacles of the Apollo missions. There were no astronauts waving from the gantry, no throngs of people holding their breath. Instead, it was a more quiet, focused affair. The Titan Centaur rocket's powerful multi-stage launch vehicles were designed to push their precious cargo beyond Earth's gravity well and set them on their interplanetary trajectories. You hear the deep resonant rumble as the engines ignite a sound that shakes you to your core. It's not a violent sound, but one of immense power, a sound of release. The two ships, separated by a little over 2 weeks, slipped the bonds of Earth and began their long, slow climb. What's a fascinating lesser-known detail about the launch is that Voyager 2's upper stage rocket suffered a brief data loss during its ascent. For a few heart-stopping moments, the team on the ground lost contact. The spacecraft was spinning too rapidly, and the ground-based computers couldn't lock onto its signal. It was a terrifying moment, a possible mission-ending failure just minutes after launch. But then, as quickly as it had begun, the anomaly resolved itself. The spacecraft's onboard systems stabilized, and it resumed its journey as if nothing had happened. It was a small early omen of the resilience and stubborn determination that would define Voyager 2's entire journey. Voyager 1's launch was, by contrast, a textbook success, clean and precise. It was almost too perfect a quiet foreshadowing of its own methodical no-frills path. From the moment they left the launch pad, they began something no other spacecraft had done before. They weren't just going to visit planets. They were going to ride a gravitational highway crafted by physics precision timing and a healthy dose of ambition. Their shared mission became a kind of tag-team exploration, each probe handing off the baton to the other as they moved farther and farther from the sun. The Voyager 1, with its quicker path, was a scout, a pioneer. It would fly to Jupiter and Saturn, take a good look, and then turn north and head out of the planetary plane, forever leaving the traditional highway. Voyager 2, on the other hand, would take the slow road, staying in the plane of the solar system, with a more leisurely cruise that would allow it to potentially visit Uranus and Neptune if all went well. The launches might have looked routine to an outsider, but to you, knowing the story, they were a profound beginning. They were the quiet opening to one of humanity's greatest journeys. It's an irony that the most far-reaching, most enduring space mission in history began with so little fanfare. Voyager didn't have the crowds of Apollo or the pageantry of a shuttle launch. It began with 2 silent liftoffs, a flurry of calculations, and a belief that precision gravity and human ingenuity could get us to places we'd never been. And as you watch the twin specks of light vanish into the sky, you feel a sense of peace. The journey has begun. The celestial pinball game is on. The balls have been launched, and now all you can do is wait. wait for the whispers of data to begin arriving from a world of swirling gas and ferocious storms, a world that is about to introduce itself to us for the very first time. You breathe deep, and you are ready. The stage is set. The long months and years between launch and arrival were a testament to patience. While the rockets roared for a few minutes, the journey to Jupiter took nearly 2 years. For you back on Earth, it was a time of quiet anticipation, a time of trusting the tiny machines you had sent into the deep. You were just a human on a spinning rock, but a small part of you was now traveling through the asteroid belt, past Mars, and into the outer reaches of the solar system. You can imagine the spacecraft now a silent, disciplined traveler, coasting through a vastness that is colder and darker than you could possibly imagine. And then the moment arrived. In March of 1979, Voyager 1 made its closest approach to Jupiter, and a few months later in July, Voyager 2 followed. For decades, Jupiter had been the king of the solar system, but it was a king seen only from a distance, its court a swirling blurry image in a telescope. But Voyager changed all of that. It peeled back the veil of mystery and showed us a world of ferocious, chaotic beauty. It was an awakening, a moment when a fuzzy point of light became a dynamic, living planet. The first thing that struck the scientists and everyone else who saw the images was just how alive Jupiter was. From a distance, its banded atmosphere looked almost serene. But as the spacecraft drew closer, the calm bands gave way to a maelstrom of activity. There were storms everywhere, swirling ovals the size of continents, jet streams roaring in opposite directions, and a vibrant canvas of colors, oranges, reds, yellows, and deep whites. It was as if the planet itself was a living, breathing work of art, and there, in all its glory, was the Great Red Spot. This legendary storm, which had been observed for centuries, was revealed in stunning, mesmerizing detail. It wasn't just a red splotch, it was a textured, swirling vortex of ammonia clouds and unknown chemistry rotating counterclockwise with a speed that made earthly hurricanes look like lazy whirlpools. It was a storm that could swallow Earth whole and still have room for dessert, a testament to the immense power of a planet that is more than 11 times wider than our own. What you might not know is that the Great Red Spot wasn't alone. Voyager's cameras captured dozens of smaller storms, little whirlpools of chaos dancing across the atmosphere. They weren't just random occurrences. They were part of a complex interconnected weather system that defied easy explanation. The academic debate still simmers about what exactly fuels these storms and what keeps the Great Red Spot going for so long. Is it fueled by deep-seated heat from the planet's core? Or is it a kind of self-sustaining atmospheric phenomenon? The answers remain elusive, a cosmic puzzle waiting to be solved. But the real mind-bending surprises weren't in the clouds. They were in the company Jupiter kept. Before Voyager, scientists knew of a handful of Jupiter's moons, but they expected them to be cold-cratered and lifeless, like our own moon. What Voyager discovered instead was a family of worlds bursting with character, each one a unique and unexpected story. First, there was Io. When Voyager 1's cameras first captured images of this moon, scientists saw something extraordinary. Plumes of material shooting up from the surface like geysers. But these weren't water vapor. They were massive sulfurous volcanic eruptions. It was a groundbreaking discovery, the first time an active volcano had ever been observed beyond Earth. Io was a chaotic mess of molten plains, sulfur lakes, and freshly formed lava flows painted in shocking yellows, reds, and oranges. It was a world of endless violent upheaval, a geologically active satellite caught in a gravitational tug-of-war between Jupiter and its neighboring moons. Then came Europa. At first glance, it appeared calmer, a smooth, icy shell with very few craters. But smoothness in space is often a clue. It suggests that the surface is being constantly refreshed, resurfaced. Voyager's images hinted at long dark lines crisscrossing Europa's surface. These weren't just cracks. They were fractures in the ice that suggested something even more profound, a subsurface liquid ocean. An ocean kept warm by the same tidal forces that powered Io's volcanoes. It was a tantalizing possibility, a whisper of a vast salty sea beneath a frozen crust, a place that to this day remains one of the most promising locations to search for life in our solar system. The discovery transformed Europa from a footnote into a front-page headline, and the Voyagers didn't stop there. They looked at Jupiter's immense magnetosphere, a region of space so vast that it would appear bigger than the full moon in our sky if you could see it. This magnetic field, 20,000 times stronger than Earth's traps, charged particles and creates intense, dangerous radiation belts that would have fried the electronics on any less shielded spacecraft. A less-known historical fact is that the Voyager team had to make last-minute adjustments to their flyby trajectories to avoid the most dangerous pockets of this radiation. They were essentially flying a tiny, delicate robot through a cosmic minefield. The Voyagers also observed the faint, dusty rings around Jupiter. Yes, rings. Though not as flashy as Saturn's, they were a surprise nonetheless. They were thin and dark, likely formed from debris kicked up by tiny meteorites, smashing into small inner moons. This discovery was a small but significant moment, a quiet reminder that the universe is full of secrets, and even the smallest details can change everything we thought we knew. As the spacecraft moved away, they sent back more and more stunning data, but perhaps the most important thing they sent was a new way of seeing. Jupiter wasn't just a big ball of gas anymore. It was a complex dynamic system filled with fascinating chemistry, ferocious weather, and an entourage of moons that could have been the stars of their own separate missions. The Voyagers didn't just confirm what we suspected. They introduced us to a family of worlds we had never imagined. You feel a sense of wonder as you watch the images come in pixel by pixel, a slow unfolding of an epic tale. You feel a profound connection to the silent, tireless machines that are sending these whispers back to us. They were so small, so simple, and yet they had just rewritten the encyclopedia from nearly 500 million miles away. The encounter with Jupiter was the first act of this grand tour, and it was a triumph. The cosmic pinball game had begun, and the first shot was a bullseye. The thunderous drama of Jupiter faded into the rearview mirror, and the journey continued. Now the Voyagers were on a path to a world of quiet elegance, a world that had been a fixture in textbooks and a silent muse for centuries. If Jupiter was a king, then Saturn was its graceful cousin, wrapped in an outfit so iconic that even a casual observer could spot it in a lineup. Its rings gleaming like cosmic jewelry had captured imaginations since Galileo first saw them. And though his telescope couldn't quite resolve them, he poetically described them as ears. By the time Voyager arrived in the early 1980s, we knew those ears were a magnificent system of rings, but we had no idea of their intricate, breathtaking complexity. You can imagine the anticipation in the control room as the first images began to arrive. The team, still buzzing with the triumphs at Jupiter, was now turning its attention to the ringed planet. Voyager 1 flew by Saturn in November of 1980, and Voyager 2 followed less than a year later in August of 1981. They came for the show, and Saturn did not disappoint. The view was breathtaking. What was once a few broad bands, a handful of circles, was revealed to be a delicate lacework of thousands of individual ringlets so perfectly thin they seemed to defy physics. These rings are made mostly of water ice, with particles ranging in size from tiny grains to house-sized chunks. They stretch more than 200,000 miles across, yet are astonishingly thin, often no more than 30 feet thick. It's like stretching a piece of paper across the length of a football field. The academic debate that continues to this day centers on how they stay so perfectly arranged and why they haven't collapsed into a single cohesive mass. Was it the gravitational influence of Saturn's moons? Was it something more subtle, more mysterious? Voyager gave us the data to start asking those questions. The cameras of Voyager peered into those rings and revealed far more than expected. The Cassini division, a dark gap that had been visible from Earth for centuries, wasn't empty at all. It contained its own set of thin, faint rings. Even more curious was the discovery of the Encke gap, a narrow division within the A-ring, and the puzzling behavior of so-called shepherd moons. These were tiny satellites whose gravitational influence helps maintain the sharp edges of the rings, acting like cosmic sheepdogs, corralling particles with invisible hands. It was as if the entire system was a living, shifting ballet of gravity and ice. And then there were the spokes. These looked like ghostly radial lines drifting across the rings, like shadows or smears. They would appear, drift, and then vanish. Scientists still aren't entirely sure what causes them. Was it magnetic interactions with Saturn's rotating field? Tiny impacts, creating brief clouds of particles? Whatever the mechanism they gave, the rings a haunted ethereal quality, a touch of unexplained beauty. This is a common historical fact of the mission, but a detail that is often glossed over in favor of the more dramatic discoveries. Saturn itself proved to be no less fascinating. Though less colorful than Jupiter, with a more uniform golden hue, its atmosphere was still active and dynamic. Bands of clouds flowed around the planet, driven by rapid rotation. A day on Saturn lasts just over 10 hours. Voyager observed jet streams, large storms, and curious hexagonal patterns near the poles. Though the full mystery of Saturn's polar hexagon wouldn't be revealed until decades later. By the Cassini mission, Voyager gave the first hints of its strange geometric symmetry. But of all the moons in Saturn, has many ones stood out as the most intriguing. Its name was Titan, and it was larger than Mercury, shrouded in a thick orange haze. A common historical fact about Titan is that Voyager's instruments detected that this atmosphere was mostly nitrogen, with traces of methane and other hydrocarbons. It was eerily similar to Earth's early atmosphere, but what you might not know is that Voyager couldn't see through the haze. Titan was shy. It revealed its size, its pressure, and its chemistry, but not its surface. Still, that was enough. An atmosphere that thick meant weather erosion, maybe even lakes or oceans. Speculation flourished. Was Titan a frozen Earth in slow motion, or a preview of what Earth might look like in a billion years? The academic debate at the time, which still resonates today, was whether to sacrifice a future flyby of Uranus and Neptune for a closer look at Titan. The decision was agonizing. A close pass of Titan meant a specific trajectory for Voyager 1-1 that would send it out of the plane of the solar system after the encounter, making a trip to Uranus and Neptune impossible. Voyager 2, with its slightly different trajectory, had the potential to keep going to the farthest planets. The team had to choose. The trade-off was calculated and deliberate, and a little bittersweet. Titan had promised too much to ignore. And so, with a metaphorical shrug, Voyager 1 took its shot, sacrificing its planetary tour for a close-up of this one mysterious world. Still, Saturn gave both spacecraft more than enough to marvel at. Beyond the rings in Titan, the system was teeming with diverse moons, each with its own personality. There was Mimas, with a giant crater that made it look suspiciously like the Death Star from the popular movie Star Wars, released just a few years earlier. There was Enceladus, a small bright moon with a surface so reflective it looked like freshly fallen snow, which, unbeknownst to anyone at the time, held its own geysers and a subsurface ocean. Voyager didn't just show us these moons, it introduced them as characters in an unfolding story. Saturn's neighborhood wasn't static. It was vibrant, strange, and deeply textured. The icy surfaces, the gravitational resonances, the whispered secrets buried beneath clouds. It all felt like an invitation to return. By the time Voyager 1 and Voyager 2 finished their Saturn encounters, they had fundamentally changed our understanding of the ringed planet and its many companions. They turned what was once a grainy point of light into a living world, rich with texture and wonder. And perhaps most impressively, They did all this with instruments designed in an era when the height of luxury was a shag carpet and a microwave oven. The spacecraft, by now many years beyond their warranty, had accomplished more than anyone had dared hope. With its job at Saturn, complete Voyager 1 bowed out, turning its antennas homeward as it began a new chapter not as a planetary explorer, but as a Voyager in the truest sense. Its planetary tour was over, but its journey into interstellar space had only just begun. Saturn, with its golden rings and swirling moons, waved farewell in the rearview mirror. Its mysteries partially unveiled its beauty, forever imprinted in Voyager's unforgettable photographs. A planet that had once been a distant enigma was now a part of humanity's story, and Voyager had given it a voice. As Voyager 1 began its slow, solitary exit from the planetary neighborhood, its twin Voyager 2 continued on its appointed course. The journey between Saturn and the next destination, Uranus, was long and lonely. We're talking years of silence, a patient coasting through billions of miles of cold, empty space. You can feel the quietness of that long drift, a profound, serene stillness that makes the years spent traveling feel like a single, peaceful breath. Voyager 2 was now our sole emissary to the two most distant planets, the forgotten siblings in the planetary family photo. To this day, it remains the only spacecraft to have visited them. First up was Uranus. Voyager 2 approached the seventh planet from the Sun in January of 1986. After the drama of Jupiter and the elegance of Saturn, Uranus felt like a disappointment at first glance. It was a pale turquoise orb, smooth and featureless, as if someone had drawn a planet with a single crayon and decided that was enough. The images came in, and the initial reaction from the public was a bit of a collective shrug. Where were the storms? Where were the swirling bands of color? But as always, Voyager's instruments peeled back the stillness and found complexity lurking beneath the calm exterior. The most striking and common historical fact about Uranus is that it is tipped over. Most planets spin like tops upright and wobbling slightly. Uranus spins like it's lounging on its side, rolling around the Sun with an axial tilt of about 98 degrees. A more subtle detail is that this tilt has strange consequences. Its seasons are extreme, with one pole facing the Sun for over 20 years, basking in constant light, while the other is plunged into shadow. At the time of Voyager's visit, the South Pole was pointed almost directly at the Sun, giving scientists a rare but oddly limited view of the planet's atmospheric dynamics. The atmosphere itself was colder than anything previously measured, a brisk 370 degrees Fahrenheit. Voyager detected faint cloud bands and signs of wind, but nothing as dramatic as Jupiter's storm systems. Later analysis would reveal that Uranus's apparent stillness was deceiving. It had winds of up to 500 miles per hour, but they were subtle, hiding beneath the haze of methane and ammonia. Then there was the magnetic field, a delightful curveball that continues to be a point of academic debate. Unlike Earth, which has a magnetic field neatly aligned with its rotation, Uranus said, "Let's do something weird." Its magnetic field is tilted nearly 60 degrees from its rotational axis and is also offset from the planet's center. It's like a bar magnet trying to play hopscotch while rolling downhill, creating a lopsided magnetosphere that wobbles and shifts as the planet spins. Scientists are still trying to figure out exactly how such a bizarre magnetic field is generated. Does it hint at a different internal structure, or is it a fluke of its sideways tilt? The questions linger. Voyager also got a close look at Uranus's moons. The spacecraft discovered 10 new ones, bringing the total to 15 at the time. The most memorable was Miranda, a small battered moon that looked like someone had tried to put a jigsaw puzzle together with pieces from 5 different sets. It had enormous cliffs, strange ridges, and deep-scarred valleys. The cliffs were more than twice the depth of the Grand Canyon, and they looked as if a great cosmic cataclysm had shattered the moon and then reassembled it. The scientific debate over Miranda's origin is ongoing. Was it a shattered and reassembled moon? Or was its surface shaped by internal tectonic processes? Miranda was small, but unforgettable. It reminded everyone that moons are not just passive rocks, but often worlds in their own right, shaped by heat gravity and time. After the Uranus flyby, Voyager 2 continued outward, heading for its final planetary target, Neptune. It had another 3 billion miles to go, an almost unfathomable distance. No pit stops, no tech support, just a tiny aging probe coasting into the deep. You can feel the loneliness of that journey, but also the sheer endurance. Voyager 2 was built for this, and it was doing it flawlessly. In August of 1989, Voyager 2 arrived at the farthest planet in our solar system, at least by classical definition. Neptune, with its deep blue color, looked strikingly beautiful. That color comes from methane in its atmosphere, which absorbs red light and reflects blue. But unlike Uranus, Neptune wasn't shy. It was dynamic, vibrant, and full of surprises. Despite being farther from the sun and receiving less light, Neptune turned out to be remarkably active. Voyager 2 discovered massive storm systems, including the now famous Great Dark Spot. This was a swirling oval storm roughly the size of Earth, complete with fast-moving winds and bright white clouds made of frozen methane. Winds on Neptune reach supersonic speeds up to 1,300 miles per hour, the fastest observed in the solar system. Exactly how Neptune generates such powerful weather, despite its cold and sparse energy input, remains a mystery and a point of ongoing academic debate. Like Uranus, Neptune's magnetic field was strange. Tilted and offset, it produced a magnetosphere that writhed and wobbled with each rotation. Voyager's instruments picked up intense radio emissions and evidence of complex interactions between the planet and the solar wind. It was as if Neptune, from its distant perch, was playing its own chaotic symphony in a key no one had heard before. And then came Triton, Neptune's largest moon, and arguably one of the most fascinating objects in the outer solar system. A common historical fact is that Triton orbits in the opposite direction of Neptune's rotation, a strong clue that it was likely a captured object, perhaps a Kuiper Belt wanderer ensnared by Neptune's gravity. A lesser-known detail is that Triton was cold, strange, and unexpectedly active. Voyager 2 saw geysers erupting from its surface, nitrogen gas, spouting several miles high from beneath a thin crust. This cryovolcanism hinted at internal heat, perhaps driven by radioactive decay or residual tidal forces. Triton even had a thin atmosphere of nitrogen, making it the only large moon besides Titan with a detectable envelope of gas. The Neptune flyby marked the end of Voyager 2's planetary tour. It was the last time any spacecraft would see a new planet up close, at least so far. After that, Voyager turned its cameras away and settled into the next phase of its life, interstellar drift. But what it left behind was remarkable. Uranus and Neptune had gone from distant blue dots to real complex worlds with moons with geysers, storms faster than sound, and a reminder that even at the edge of the solar system, nature never stops surprising us. Voyager 2 didn't just extend the mission. It redefined what was possible. It taught us that the most remote places can hold the richest stories if we're willing to go far enough to hear them. And that sometimes, if you're very lucky and very precise, a little probe launched in the disco era can rewrite the encyclopedia from 3 billion miles away. After its triumphant tour of Jupiter and Saturn, Voyager 1 had a new job. It was no longer a planetary explorer. It was a silent drifter. It continued its journey outward, leaving the familiar orbits of the planets and heading into the vast, quiet blackness of space. The years passed in a peaceful silence, a long, slow coast away from the sun's warmth. But even in this solitude, its story was not yet finished. It had one final profound act to perform. It had one last picture to take. The idea was simple in concept, but bold in spirit. Turn Voyager's cameras back toward Earth and snap a snapshot from the edge of the solar system. a family portrait of sorts, the sun and its planets, seen from billions of miles away. The idea was not driven by science, but by philosophy. It was Carl Sagan, ever the poetic advocate for cosmic perspective, who pushed hardest for the idea. He had long believed that such a photograph could offer a rare and powerful moment of reflection, a visual reminder of our small place in the universe. There was, as you might imagine, some resistance to the plan. The engineers were understandably cautious. Voyager's cameras, designed for close-up shots of planets, were not meant to point near the sun even from that immense distance. A misstep could have damaged sensitive equipment, or at the very least wasted precious power. A common historical fact is that the Voyager camera system was already being retired from regular use, and a good portion of the mission team saw no value in risking it for a philosophical gesture. But by 1990, the risk was minimal, and the push from Sagan's team was relentless. The gesture, they argued, was more important than the risk. So on February 14th of that year, Valentine's Day, NASA gave the go-ahead. Commands were sent, the spacecraft rotated, and the shutter clicked. The result was, at first glance, not particularly dramatic. In one of the images, Earth appeared as a tiny pale blue dot, less than a pixel wide, caught in a shaft of scattered sunlight. It floated against the darkness of space, almost lost in the static. If you didn't know what you were looking at, you might have missed it entirely. But when you understood what you were seeing, it became one of the most profound photographs ever taken. That faint speck was Earth. Home. Everyone you've ever known, every civilization, every story, every joy and every sorrow, all contained within a single shimmering mote of light. From nearly 4 billion miles away, our planet was reduced to a whisper. Carl Sagan later reflected on this image in what became one of the most moving passages in the history of science communication. In his book, Pale Blue Dot, he wrote, "Look again at that dot. That's here, that's home, that's us." He reminded us of the folly of human arrogance, the endless battles we fight over borders and ideologies, the importance of kindness, of preserving our fragile planet. He urged us to recognize that from a cosmic perspective, we are all riding the same speck of dust through an indifferent universe. Interestingly, Earth wasn't the only object captured in that family portrait. Voyager's cameras also snapped images of Neptune, Uranus, Saturn, Jupiter, and Venus, all tiny specks of light themselves. Mercury was too close to the sun to be seen, and Mars didn't show up well due to the angle and glare. But Earth, that pale blue dot, stole the show. A lesser-known detail about this image is that the bright streak of light running through it is not a cosmic ray or a distant star. It's a trick of the light, a shaft of sunlight scattered by the camera's optics. It is in a way a photographic imperfection that only adds to the poetic, dreamlike quality of the image. The academic debate that continues to this day is a philosophical one. Did the pale blue dot truly change humanity's perspective as Sagan hoped? Or was it just a beautiful image, a fleeting moment of reflection that was quickly forgotten as we returned to our daily squabbles? Some historians argue that the image has become a powerful symbol for environmentalism and international cooperation, a silent reminder of our shared destiny. Others believe that for all its poetry, it hasn't fundamentally changed our behavior as a species. The debate is a quiet one, but it speaks to the very heart of the mission. Can a machine, can a photograph inspire us to be better? After the images were taken, the cameras were powered off for good. Voyager would continue collecting scientific data with other instruments, but it would never take another photograph. In that way, the pale blue dot image was Voyager's farewell, not just to the planets it had visited, but to visual observation itself. A final look back, a gentle turning of the gaze, before heading into the long silence of interstellar space. You can feel the weight of that final shutter click. It wasn't the sound of a camera. It was the sound of a chapter closing. The story of planetary exploration was over for this magnificent little machine. Now it was just a traveler, a drifter, a silent sentinel. But in that one moment, It had given humanity a gift that no other mission had offered perspective. It's easy in day-to-day life to lose sight of the big picture, to get caught up in small dramas and deadlines. But every now and then, a single pixel can change how we see everything. That was the power of the pale blue dot. It didn't just show us Earth, it reminded us to cherish it. Voyager 1 didn't need to take that image. Its scientific mission was already over. But that photograph and the reflection it inspired became one of the most enduring legacies of the entire mission. It's still out there. That little spacecraft still moving farther away, still whispering data back to Earth. And Earth still spinning, still dreaming, still tucked inside that pale dot. In the end, the pale blue dot wasn't just a photo. It was a reminder that even in the vastness of space, a tiny world can hold infinite meaning. You are now floating with Voyager 1 past the orbit of Neptune, beyond the lonely icy realm of Pluto. The planets are gone. The sun, once a searing furnace, is now just the brightest star in a sky full of them. You are in a place where light takes hours, not minutes, to reach you. And here in this quiet, cold darkness, you are approaching the final invisible frontier. A border you can't see, but one that you will know when you cross it. This is the edge of our home, and it's called the heliopause. To understand what the heliopause is, you have to think of our sun not just as a light bulb, but as a kind of cosmic wind machine. It constantly sends out a stream of charged particles known as the solar wind, which blows outward in all directions. This solar wind carves out a massive bubble around our entire solar system. This bubble, our home, is called the heliosphere. Inside it, the sun is in charge. Its magnetic field shapes the space environment, its particles fill the void, and everything dances to its tune. But eventually, that influence has to run out. The solar wind, after traveling billions of miles, begins to weaken as it pushes against the material between the stars, a cold, sparse mixture of gas dust and cosmic rays, known as the interstellar medium. The heliopause is the boundary where the pressure from the solar wind finally gives way to the pressure of the interstellar medium. It is the outer skin of the sun's protective bubble. Beyond that, the galactic wilderness begins. For decades, scientists had predicted where this boundary might be, but no one had ever visited it. It was a theoretical line drawn on a map, a subject of academic debate and speculation. There was no glowing sign that said, "You are now leaving the solar system." It was more like a shifting, wobbly, invisible frontier, constantly changing depending on the solar cycle, local density, and magnetic conditions. A common historical fact is that in August of 2012, NASA made an extraordinary announcement. Voyager 1 had crossed the heliopause and entered interstellar space. After more than 35 years of travel, it had officially left the sun's domain. But the journey across wasn't a sudden event. It was a slow, gradual process, and the signs were subtle. You, as the silent observer, can feel the changes now. Inside the heliosphere, you are surrounded by solar particles, a steady stream of protons and electrons thrown off by the sun. But as you move outward, you begin to detect a drop in those solar particles and a simultaneous dramatic increase in cosmic rays, high-energy particles coming from outside the solar system. It's like leaving a crowded room and entering a quiet, dark forest. The familiar noises fade, and a new ambient hum begins to grow. This was a major red flag, or in this case, a green light, telling the scientists on Earth that Voyager was in a new and different environment. But that wasn't enough for some. The academic debate that swirled around the announcement was intense. Scientists expected the direction of the magnetic field to shift dramatically once Voyager entered interstellar space, but that didn't happen immediately. The field changed subtly, but not in the way the models had predicted. Had Voyager truly crossed the boundary, or was it just in a strange, turbulent region of the heliosphere? The question lingered for months, a frustrating silence in the data. The answer came in the form of a lesser-known, but brilliant detail: a lucky solar outburst. In March of 2012, The Sun had released a coronal mass ejection, a huge wave of charged particles, which eventually caught up to Voyager more than a year later. When that shock wave reached the spacecraft in April of 2013, Voyager's instruments recorded a sudden oscillation in the surrounding plasma, allowing scientists to measure the density of the space around it. What they found was striking. The plasma density had jumped by a factor of 40, indicating that Voyager was now in a much denser region, the interstellar medium. That sealed it. The spacecraft had truly crossed the heliopause. It's worth noting that while Voyager 1 entered interstellar space, it didn't leave the solar system entirely. The Sun's gravitational pull extends far beyond the heliopause, past the Kuiper belt, and deep into a distant region known as the Oort cloud. That cloud, a theoretical shell of icy bodies, could stretch halfway to the nearest star. Voyager, moving at more than 38,000 miles per hour, won't reach the inner edge of the Oort cloud for another 300 years, and it won't exit it for another 30,000. So yes, technically, you are still within the Sun's gravitational neighborhood, but you are beyond the Sun's influence in every other way. You have entered the galactic wilderness. Voyager 2 followed its sibling into interstellar space in November of 2018. Although it took a different route and encountered slightly different conditions, it provided valuable confirmation of Voyager 1's findings. For the first time, we had not one, but two data points from the edge of the Sun's domain. It was a rare opportunity in a science where single missions are usually all we get. Crossing the heliopause didn't reveal dramatic new landscapes or glowing interstellar clouds. There were no space whales or alien billboards. But what Voyager found was in its own quiet way profound. The interstellar medium is colder, denser, and more complex than previously imagined. It hums with low-frequency waves and is shaped by magnetic forces that reach across light years. And perhaps most poignantly, the crossing marked a symbolic boundary as much as a scientific one. Voyager had officially gone from being a planetary mission to being a galactic one. It had become an interstellar traveler. You are there now, a small silent part of this historic moment. You feel the deep serene cold, a cold so pure it is almost a warmth. You are the first to feel this. You are the first to be here. Voyager is not headed to any particular star. Its trajectory will take it slowly through the Milky Way, perhaps, passing within a few light years of a distant sun in 40,000 years. By then, Earth's continents will have shifted, languages will have changed, and Voyager's signal will have long gone silent. But the spacecraft will still be out there intact, drifting between stars, a tiny piece of human craftsmanship, sailing through an unimaginable sea. And it's still talking to us faintly, patiently. A signal so weak that it takes more than 17 hours to reach Earth. But it comes through a whisper from beyond the sun, telling us about magnetic fields and particle density and the subtle nature of the interstellar breeze. Crossing the heliopause didn't make front-page news for long, but it was one of the most important thresholds humanity has ever crossed. It marked the beginning of a new chapter, not just for space exploration, but for how we see ourselves. Voyager left the warmth of the solar bubble and entered the cold, quiet dark. And it kept going. You are now in the great cold silence of interstellar space, drifting with the Voyagers. The sun is a bright star in the distance, but its warmth is a memory. The planets are gone. There is only the hum of the interstellar medium and the faint, persistent whisper of data. But if you were to lean in close, very close, you might just hear the soft ticking of time catching up. Their power is fading slowly, inevitably. Like old lanterns burning their final drops of oil, the Voyagers are beginning their long goodbye. From the very start, the Voyagers were powered by something quite special. Radioisotope thermoelectric generators, or RTGs for short. These devices use the heat from decaying plutonium-238 to generate electricity. Unlike solar panels, which get increasingly ineffective the farther you travel from the sun, RTGs keep humming regardless of distance. But even RTGs have a shelf life. Plutonium-238 decays at a steady, predictable rate, which means the power output has been decreasing year by year. A common historical fact is that at launch in 1977, each Voyager's RTGs generated around 470 watts of power. Today, nearly 50 years later, the output has dropped to less than half of that, and it's still falling. What makes this particularly tricky is that Voyager isn't just a box with an on switch. It's a complex machine with many parts that all need power instruments: heaters, transmitters, memory systems, attitude control. As the available power dwindles, choices must be made. Which systems are essential, and which ones can go dark? NASA's engineering team has been managing this balancing act with a mix of creativity, caution, and a little bit of magic. They've gradually turned off instruments one by one, not because the instruments themselves are broken, but because there simply isn't enough juice to keep them running. Each time one is powered off, it's a small moment of mourning for the mission team. A lesser-known detail about this process is that in 2023, Voyager 2's plasma science instrument was deactivated. That tool had been monitoring the density and temperature of particles in space, helping researchers map out the edge of the heliosphere. Its loss was keenly felt but necessary. And it's not just about the science instruments. The spacecraft must also keep themselves warm. Interstellar space isn't just cold. It's bone-deep freezing with temperatures nearing absolute zero. The RTGs produce some heat, which helps, but small heaters are strategically placed throughout the spacecraft to prevent key systems from freezing. Those heaters consume power too, and they're being turned off selectively. Some parts of the spacecraft are now operating well below their original temperature specifications, held together by a combination of clever engineering and stubbornness. The academic debate that lingers now is a heartbreaking one. What will be the last system to be turned off? Will it be the transmitter, or will it be the last remaining heater? The decision is not a matter of science, but of philosophy. But while the end is visible on the horizon, it's not here yet. Engineers have been finding clever ways to stretch the remaining power. One recent trick involved tapping into a small onboard voltage regulator that had never been used before. It wasn't much, but it bought time. And even with their fading strength, the Voyagers are still sending valuable data. They're still contributing to our understanding of cosmic rays, solar influence, and the nature of space beyond the heliosphere. The quality of the data hasn't diminished, only the volume. Each bit of information takes longer to send. Each packet is more carefully curated, but it still arrives clean and sharp from billions of miles away. It's worth remembering that most space missions don't last this long. They're designed for months, maybe a few years. Voyager was expected to last 5 years at best. Its current age is a kind of engineering miracle, not because it defied physics, but because it was built to last, and because the people who've maintained it never stopped caring. Behind the scenes, there's a small but dedicated team at NASA's Jet Propulsion Laboratory who monitor the Voyagers every day. They craft each command sequence with extraordinary care, double-checking every line of code before transmitting it across the solar system. At the current distance, it takes about 22 hours for a signal to reach Voyager 1 and another 22 to hear if it responded. Imagine trying to troubleshoot a problem with your car, but every message to the mechanic takes nearly 2 days. That's what the team deals with day in and day out. Eventually, sometime in the next few years, the power output will fall below what's needed to run even the bare minimum systems. The transmitters will shut off. The spacecraft will go silent. There will be no explosion, no dramatic farewell. Just a long pause in a signal that never resumes. But even then, the spacecraft will not be lost. They will keep traveling at over 35,000 miles per hour. Long after they fall silent, long after Earth loses contact, Voyager 1 and Voyager 2 will continue their journey. In about 40,000 years, Voyager 1 will pass within a light year or two of a small star called Gliese V945. Voyager 2 will drift in a slightly different direction, not approaching any known star for perhaps even longer. They're not on a collision course with anything, just quiet, eternal travelers in the dark, and they still carry their golden records. Time capsules etched in gold containing music greetings and the sounds of Earth. If some distant civilization ever finds them, they'll discover a tiny artifact of our species, a message from a long-gone world saying, "We were here." For now, though, the Voyagers are still very much with us. Their signals still reach the Deep Space Network. Their data still appears on scientists' screens. And their mission, a mission of discovery, endurance, and wonder, continues. They remind us that exploration doesn't always need a destination. Sometimes, just going, just reaching, just listening, that's enough. Even in the fading light, they are beacons. And as long as they keep speaking, we'll be listening. In the chill of interstellar space, where the sun is just another bright dot and the background hum of the universe grows louder, Voyager 1 and Voyager 2 continue their long flight into the dark. But if you were to lean in, close, very close, you might just hear the soft ticking of time catching up. Their power is fading slowly, inevitably. Like old lanterns burning their final drops of oil, the Voyagers are beginning their long goodbye. They were born in a world of rotary phones and disco balls, handwritten code and slide rules. They've flown through solar flares, radiation belts, and the ever-thinning edge of the sun's influence. They've seen worlds we once only guessed at and sent back evidence of geysers, volcanoes, rings, and oceans. And now, with just a few instruments still warm, they continue into the vast silence. But it isn't really silence they move through. It's just too quiet for ears to notice. The space beyond the solar system hums with charged particles and ripples of ancient starlight. It's a place where atoms drift for eons without meeting, where distance loses all practical meaning, and where time itself stretches out like a road without signs. And yet, in the middle of all that quiet, something human is there. A piece of us wrapped in metal and gold, humming softly with fading power and carrying a message we wrote long ago. It's easy to forget how extraordinary that is. We built these spacecraft to explore the outer planets. That was their job, their assignment, their scope. But the moment they passed those final planetary encounters, they became something more. Not because they changed, but because we did. We realized they were no longer just tools. They were storytellers, pilgrims' time capsules, cosmic postcards with no return address. Voyager's journey is in many ways a metaphor for what it means to be human. To ask questions that have no clear answers. To build things that will outlive us. To wonder not for profit or conquest, but for curiosity, for the sheer joy of seeing what's out there. The spacecraft aren't fast. They're not flashy. They're not built to impress, but they persist. And there's a quiet dignity in that. One day soon, Voyager's power will finally run out. The signal will fade. The instruments will fall silent. No one will notice immediately. There will be no explosion, no dramatic farewell, not just a long pause in a signal that never resumes. But even then, the spacecraft will not be lost. They will keep moving slowly and steadily among the stars, silent, but not forgotten. And someone, perhaps us, perhaps not, might remember that we once built 2 small ships and sent them into the dark, not for answers, but for the joy of the question. And maybe that's all the legacy we need.